Here we look at Pascal's principle. And whether or not you know it, you use Pascal's principle on a basically daily basis. So Pascal's principle basically states a change in pressure applied to an enclosed fluid is transmitted undiminished to all portions of the fluid and to the walls of the container. This just means that typically fluids, when you change the pressure, it goes everywhere. So if you ever tried to squeeze a water balloon, when you put an enclosed fluid, when you squeeze a water balloon, that water balloon starts to bulge out in other areas. You increase the pressure on the walls of that balloon. Toothpaste out of a tube, right? You squeeze one end of the tube, toothpaste comes out the other end. That's Pascal's principle. The force you apply in one end of the tube of toothpaste is transmitted throughout the entire fluid, all the toothpaste in the tube, and the walls of the container, which forces it out the other end. Hydraulic systems in your car, your brake system, right? You can stop a multi-ton vehicle by gently pressing on a brake pedal. That brake pedal is actually a fluid system. It's a hydraulic system. It sends pressure, a force, to your discs on your brakes, applying those discs and stopping your vehicle. So Pascal's principle allows us to create a very simple hydraulic machine that can be used to amplify the force of a user. So let's look at a very simple example here. We have fluid below. So this is filled with some kind of a fluid. It has to be incompressible. Incompressible just means that you can't easily squeeze it. So air would be a poor example of this for Pascal's principle, but water is fairly incompressible, or brake fluid or something like that. So here we have, imagine this is a tube, a cylinder, a narrow cylinder up here on the left, and a wide fat cylinder up here on the right. And sitting on top of the fluid on both sides is a piston that can move up and down. So this black piece is a piston that's free to move up and down. No water can sneak out the sides. But if you push down on this piston, you're displacing this fluid. Where does it go? Well, it can't be compressed, so it goes to push up on this end. Right? The fluid has to go somewhere. So, since these are the same depth, P1, the pressure here at the bottom side of this piston, and P2, the pressure on the bottom side of the piston on the right, are at the same depth, so those pressures should be the same. Well, pressure is force over area. So P1 is F1 over A1, where A1 is the area of the piston, so some small circle on the bottom of this piston that's being pushed down. P2 is F2 over A2, where A2 is a much larger diameter piston, more surface area pushing down on the fluid. Well, if you rearrange this equation, what you see is that the force out of this right-hand side, this side number 2, is equal to the force applied on side number 1 times the ratio of the areas. So if area 2 here is much, much, much larger than area 1, force 2 is much larger than force 1. You can cheat. You get magnified forces. So this is how hydraulic jacks work. Why you can pump up a jack with your hand and it lifts a car. Or how brake pedals work. By applying a push on a brake pedal, you can apply a significant amount of force on the disc brakes of your car, slowing this speeding vehicle. Think about it. I mean, a single foot can stop a vehicle with this type of a system. Otherwise, you have to do the old Fred Flintstone, right? Imagine your brake lines go out. You can't just stick your foot out, put it on the ground, and expect to stop as quickly. While the force is magnified, the work done is not. So this is not a way of getting free work out, right? Work is energy. Energy has to come from somewhere. So if we could create free work this way, we could create free energy. Well, how is work conserved? Well, work is force times distance. Hopefully you can see that if I apply this force, I have to move this through a much, 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 much larger distance to displace the fluid in this small cylinder. If I push this all the way down, all of this fluid gets displaced here. but this is a much larger surface area, so this cylinder, this piston will go up a much smaller distance. So for example, if the force out of here is twice as big as the force in area 1, F2 will only go up half the distance. So that's one of the reasons if you've ever used a hydraulic jack, you have to pump it and pump it and pump it and pump it and pump it to get your car to go up a very, very small amount. Or in the case of disc brakes are very, very close. The brake pads are very, very close to the disc brakes. So when you push on the gas pedal some distance, some large distance, the brake pads only have to go a very short distance before they push on the disc brakes or the drums, causing the car to slow. So Pascal's principle explains why your heart works, right? For those in the medical profession, it's a closed system. Your circulatory system is a closed system, right? When your heart pumps, it increases the pressure, which pushes blood throughout your entire system. If this didn't work, if Pascal's principle wasn't a thing, if pressure applied at one point in an enclosed fluid didn't go everywhere else, we wouldn't be alive, right? Our heart wouldn't work. Water systems in the world, wouldn't work. That's how water towers, we put water up on big towers. That creates a large amount of pressure because you live underneath the water tower. That height difference gives you pressure, water pressure, and that water pressure is sent around the community in that closed fluid system. Now this only works for closed systems, not open systems, right? No matter how many times you go to a swimming pool and you try to push down on one side of the water, the other side of the water doesn't raise up. It has to be an enclosed system.